So thank you. So I'll step on what Ron was saying on going from very high, very detailed, super resolved currents to something which may be a broader scale and more applicable to people looking at the tropical ocean, which are still orphaned from altimeters that are not giving them the full current and stuff like this. And so this presentation is pretty much a follow-up, or most of it was shown at the Azores meeting, so I'll just an extra few slides. Some of it is a bit outdated, so you actually will get more results with the simulations from Clément Hubelman, who's still working on that. He will show you that on Friday. We're working on campaigns that was just mentioned by Craig, and so going to be a talk by Louis-Marie on the campaign effort. And if that doesn't work, just go back to the PPT. So we'll get there. So, so in a few words, so SKIM is sea surface kinematics multiscale monitoring mission. So it's an ESA Earth Explorer 9 mission. So it's a candidate for Earth Explorer 9. So as Craig said, there's 2 missions that have been pre-selected. And we will see who actually gets to launch next year. And the idea that we really need to fine-tune the goals and the details of the mission. We're still work on the orbit, working on the beams, working on many different technical aspects of the mission to make it fit as much as possible a wide range of scientific objectives and also fit within budgets and other constraints. And so this work is done with a lot of people, that's people from the Mission Advisory Group, people from the SKIM team at ESA, so Craig is leading that on the science side, and Eric De Witt is more on the system side. And there's, of course, I also want to thank CNES for the support. Actually, funding for this conference is all supported by CNES, and many other things. So scientific goals, a few things about mission status, where we are, how SKIM works. I guess maybe of you still haven't heard about how that is detailed. So there actually will be a poster tomorrow by Eric Cobé on the instrument. There's a very important item on the space-time sampling. So you'll hear about different missions that have very different space-time sampling. So we'll also hear from Ernesto about WaCM, which is a very different swath and very different philosophy of measuring things, even though it's also working with the Doppler. And the link between SKIM and altimetry, and in a way, SKIM is stepping across the river, and we have 1 foot on the altimetry, and we're trying to get across the river to measure currents with new techniques. And I think there's a very interesting thing by having the nadir altimeter with the traditional measurements together with the other beams that will certainly help the use of the data. So the SKIM goals is to really explore ocean surface velocities. That includes currents, ice drift, and waves, and goes from the tropics to the marginalized zones, so most of the oceans. And also looking at wave interactions and things like surface drift. So just a few words about that. I'm really not the expert on this, so I'm looking forward to Sophie Cravat to discuss more the tropical implication of that. But these are some slides essentially from our colleagues from Guiomar in Germany, showing essentially issues with the cold water tongue in the tropical Atlantic. So you have this tongue of cold waters. This is SST temperature map. There's a couple moorings here and there. And this tongue has some nice meanders on the north side of it, which is associated with tropical instability waves. And these waves and these motions are very important for setting up the heat balance at the tropics. And the heat budget is also what's going to drive fluxes of Earth interactions, moisture fluxes, and the African monsoon and then rain and all that stuff on the African continent. So today, this transport of heat and other things across the equatorial region is very poorly constrained from observations and models. So this is some examples from a paper by Schlund et al. Showing time series over 1 year of the OSCAR product, which is a blend of altimetry and winds, ADCP measurements at a given point, I think it's right there, and the red line is the Mercator model. And so you can see the range from minus half a meter per second to plus half a meter per second. And the model's observations just don't catch this variability of the currents in the tropics. This is looking at slightly, that's U components, is a V component, so this zonal east-west component is north-south. And you can see the same kind of thing, that the patterns which are observed locally in situ with ADCP are very far off from what can be estimated from other means today. So we really have no control on the tropical circulation today from, except for in-situ sensors. Looking at the other extreme on the planet, the marginalized zone, this is just a map going to give some examples. So this is an optical picture showing you can see the ice flows here, and this is the marginalized zone with all these mushy small pieces of ice which are vectored by the currents and make these nice meanders. And what you see here are streaks due to clouds seen over open water. So you have cold air blowing from the ice to the open ocean, and it makes some convection in the water. And so what you see here is that we can actually get some drift of the ice measurements from SAR correlation images, but the region where these images don't correlate so well is very active with very strong currents, a lot of impact of waves on the ice, and this is a place where we have no data on currents or ice drift today. And this region is going to evolve very much by 2030. We expect to have a much wider marginalized zone in the Arctic, so the Arctic is changing very fast and really needs some observation to explore these changes and get the best information for the Arctic. And finally, some words about wave interactions, showing you what we can do today using satellite altimetry derived currents, which is coming from the Aviso geostrophic currents. And you can compute some wave propagation over that. And if you make maps of the gradient of the wave heights over this region and you do an average of 1 month, you get this kind of map with very relatively small gradients. If you actually run a very high resolution model with no assimilation, so it doesn't have the eddies in the right place, but it has probably the right structure in terms of intensity of the front and the velocities, you can see that the Agulhas current here along South Africa is much sharper and much stronger. Mind the scale here from 1 meter per second to 2 meters per second. So it's a much sharper and stronger current here, which has a very strong impact on the waves. And this impact on the waves, we can actually measure it today from the altimeters. So if you actually look at gradients in wave height in the altimeters, you actually get a very good knowledge on the position and the strength of these current fronts by their effect on the waves. And so there's a lot of potential for looking at extreme waves in these currents that we today have a problem if we just use the currents from the altimeter because they're on a very small, very large scale instead of these very high resolutions. And these, of course, have some impact on shipping and other activities at sea. And this is a typical ship destroyed by a freak wave in the Agulhas current some years ago. And last word about drift. Anything at the surface, plastics, plankton, kelp. This is an example, recent paper of kelp found. So these large algae were found in a small island of the coast of the peninsula in Antarctic. And these were sampled and found to be coming from this other island across the polar front. And if you just do eddies and geostrophic currents, you never get stuff to cross the polar front, and you actually need the waves also to cross the front. So we actually need to measure both the waves and the current to address the issues of drift and dispersion for biological stuff or plastics or anything. All right, so where we are today with SKIM, as was mentioned by Craig, this thing's got moved here. So basically, where the ESA has this program of Earth explorers. There's been 8 selected so far. The first one was Gochi, SMOS, then Cryosat, and the last one to be launched was Aeolus in August. Maybe you've seen that. It's a wonderful mission measuring, it's a Doppler LiDAR for measuring winds in the atmosphere. And what we're looking forward for EE9 is a choice between Forum and SKIM. That's to be decided next year. And really, the science community is involved in this process. So you have your voice. You can play a part in this selection. And this will be done through some consultation meeting next year in Cambridge. So where we are now, so we actually have a lot of work to do right now. So this is the timeline for getting us to selection in July next year, and then launch in 2025 if everything goes fine. So there's a lot of work on the industry side, work on the instruments, the design, the mission, work on the science side, and we have to produce this report for next year. And at some point, you will be involved in this process through the consultation meeting. But also, you can also contribute now by asking the tough questions about how does it work, is it actually useful? Because for all of you that are members of ESA member states, if you are citizens of these member states, it's your taxpayer money. If you think this mission is useful, or if you think it's garbage, just let us know now, because we might as well spend our money wisely. And of course, you can always join us at the UCM next year in July. But asking questions now is a good way to go forward. So how SKIM works, in a few words, So SKIM is a combination of a classical radar altimeter with an added disco ball to make it a bit fancy, and a speed gun to measure velocities. And so the story of the disco ball is that instead of, on top of having a usual nadir beam looking straight down, like from the satellite straight on the surface, we also have beams looking to the sides and turning around the nadir, making some funny pattern on the surface. And so we're looking at straight down and also 6 degrees and 12 degrees incidence. And so the usual question I get, so how come you just look at 12 degrees incidence where the current is horizontal? Okay, right, yeah, so it's better to look horizontally to measure horizontal currents, but the backscatter from the sea surface horizontally is actually pretty weak. So there's an interesting trade-off and yeah, there's that. And also there's, okay, oops, there's kind of funny thing here. I had the link. Yes, not good. Not good? Maybe I should. So I had this stupid link here. No, it's not there. Everything goes up. So okay, so we have these different beams. So we're sending pulses at the nadir, then 12 degrees, and the different beams at 6 degrees, 12 degrees, 6 degrees, and that allows us to fill a swath which is 300 kilometers wide with measurements of velocities. And as Bertrand introduced, so this is typically the scale of one footprint on the ground. So one footprint of SKIM will be like 6 kilometer diameter, and that's very comparable to X-band radar on a ship. And you can expect this kind of gradient in velocities within the footprint, and we should be able to measure this kind of gradient. This is a simulation of, well, this is time versus the range, but it's more or less the same kind of scale. So the velocities will actually be containing a lot of waves. So we'll actually want to measure these waves, because the velocity we're measuring, as Bertrand was pointing to, contains both waves and currents. And whatever we do with Doppler measurements, we will always have these wave and currents. So we'd better know in details the wave part to be able to subtract it off and measure the current. And we have a lot of experience from that based on Envisat. And we found from theory actually that the measurement at 12 degrees on SKIM is very much like the 26-degree measurements in C-band that we got from Envisat. And the maps we got from Envisat is like this. On global scales, we have velocities from +3 to -3 meter per second, and this map doesn't look like currents at all, except maybe for the tropical part here, because this actually is a signature of the wave, which are driven by the wind. And if you actually remove this wave contribution, then you can actually look at this nice Gulf Stream example, in which you have the nice current. So red is flowing one way and blue is flowing the other way. So we have a nice model and theoretical validation for that. So there's a lot of measurements done with AirSWAT that support these measurements. This concept of the separation between waves and currents, and we'll do actually more measurements as part of the SKIM campaign in November. A few things about sampling, and I'll finish with this kind of stuff. Basically, the currents we're thinking about on the surface of the globe are typically what we use to look at these maps from models. This is from the CMEMS model. It's driven by density gradients, winds, tide, and what have you. If you look at the spatial time scale, you have this kind of map of front-end filaments, eddies, large-scale tropical instability waves. And where we sit with SKIM is typically resolving this box in space and time by having a swath which is 300 kilometer wide. We have a repeat cycle, typically every 4 to 10 days, depending on the latitude, and at high latitudes even around 1 day. And we should be able to resolve everything shorter than 60 kilometers at a time scale, which could be 4 days, 5 days, or 10 days at the equator. That's the space-time full coverage. Of course, a single SKIM pass would be a snapshot at a relatively higher resolution, but it's only a snapshot. And because all these motions are evolving fast, we have the issue of, okay, in particular, the near-initial currents that are containing a lot of energy at the surface of the ocean. And how we are aliasing these measurements and what would be impact on the system is very much something that we're looking at now. And of course, the single footprint will be resolving down to 10 meters in range direction. So we'll be measuring waves and their motion at this very high resolution. But we have a gap in our spectrum. So we're measuring this on the single footprint. Then the multiple footprints, we don't see anything between 5 kilometers and 20 kilometers, and we have this blind spot. And then we actually see the larger scale. So this is what we call SKIM a multi-scale measurement. So in terms of coverage, we're looking at different orbits, different choices possible. So this is one choice, flying together with METOP SGB, which would have some advantages of having also wind measurements and other flagging possibilities with radiometers to look at different issues of rain and cloud together with current measurements. The bad drawback with that is that at some point, right around the equator, the maximum revisit time may be a bit long, but okay, there's some other trade-off to look at. And we look at mid-latitudes, the maximum revisit time is somewhere around 5 days, and the average is something like 4 days. And as you go to the high latitudes, typically from 72 north, you're coming back every day at the same spot. So we looked at different orbits. S3 is actually a bit worse for these kind of things. There's maybe other benefits for other things, and we have to look at issues with rain and things. Just one slide about these inertial oscillations. So we have this fast oscillation of the currents. So if you go to 21 north, the inertial period is something like 35 hours. And so we're not going to be able to resolve the variation in time of this. But okay, these oscillations are more or less well resolved by today's models. But you can see that the mean value is actually off. And so we're more looking at the mean agiostrophic circulation on these few days time scale than just the inertial oscillation themselves, and that's something which today is really not well resolved. And this is just another example at the equator, where 15 days you have the measurements at the Pirata buoy and the model. So the V component is more or less okay, but the U component could really be on a different planet. So right now we really don't know the currents at the equator, and we actually know the winds on Mars better than the currents in the tropics. That's the main message here. So it's time to look at the planet, or our planet, and map these currents at the equator. And at the equator, there's issues with diurnal cycles. So we're looking at different orbits, possibly 9 a.m., 9 p.m. to be able to fly with METOP. We may have to move to 6 a.m., 6 p.m., but then we have a strong diurnal cycle with this is a time 0 and midnight local time. That's in the tropical Pacific. And you have the cycle of the velocities, and you see you have the jet in the afternoon because you have warming at the surface, so the wind is blowing on the surface, and you have this shallower layer which is going faster. And so that's something we have to keep in mind where we're actually mapping these currents, that the ascending and descending passes will be seeing very different currents in the tropics due to these things. So flying at 6 a.m., 6 p.m. would maximize this difference. Flying at 9 a.m., 9 p.m. would minimize that, and that's something we have to keep in mind. There's also issue with rain and clouds because we're working with the K-band radar, which has some issue with rain, as everybody knows. All right, the performance, I will not discuss that because that will be covered by Clément Hubelmann in his talk on Friday. But basically, the story, it's all about the white width of the swath, and Ernesto will show that very nicely. If you have a very wide swath, but even with noisy data, you can actually map much better in time the evolution of the currents. It's just to give you in perspective a modeled current, a SKIM sampling, and you can see that the small scale is not resolved, but you can get the nice ring eddy and the current. And if you map it with swaths, because the swath is much narrower, that's something, yeah. So that will be Clément's talk on Friday. We're doing some nice job together with altimetry. I will just conclude. So that SKIM is retargeted to provide new measurements of surface velocities, total surface velocity looking at currents, waves, and ice drift from the tropical currents all the way to the marginalized zone. And also, I didn't insist much on that, but it's going to be a much better measurement of waves by resolving waves down to 30-meter wavelengths, which will go much beyond what CFOSAT is supposed to do. 20 meter, okay, we'll have to prove that. And CFOSAT, by the way, is due for launch this month, so we'll learn a lot from CFOSAT in terms of wave measurements, and we will benefit a lot from the CFOSAT experience for that. Thank you.
Thank you, Fabrice. Questions to Fabrice?
That's true.
Yeah.
Maybe a comment? Since you're eager to fly with METOP because of the scatometer,
And the radiometer, yeah.
And the radiometer, yeah. Anything between 6 and 9:30, this is pretty well covered by scatometers and some radiometers as well. So if you're thinking of 6 a.m., now there's new missions also.
Yeah.
7 as well. You have CFOSAT.
But in terms of programmatics, there's operational missions which we know about METOP, so it's well lined up. But we can discuss that, and of course, any other opportunity. Maybe with other constraints on the system side will be something that we'll end up doing, but we're still looking at the different options at different times, yes.
Yeah, for sure the continuity of METOP is at 930 is not guaranteed at 6 or 7 right now, as far as I understand.
And there's just a funny sampling in time of how the beams are dancing around and sampling the currents, and you can see the radial measurements of the currents in color, which are projections of the black arrows are the true current, and each beam is getting this time series that it's turning around, which is it's not for the epileptic, sorry.
Any more questions? Okay.